In this video, we will discuss mass action law, or sometimes it is called law of mass action. And the way I remember this mass action law is N times P is equal to Ni square. This is mass action law pretty much. But in general, when people see this, they simply say, oh, this is true for intrinsic semiconductor. Mass action law states that this equation is also true for extrinsic semiconductor. Extrinsic, I mean N-type semiconductor or P-type semiconductor. So let us see why this is true. So let's say we have an intrinsic semiconductor. And in intrinsic semiconductor, we know that the electron concentration in conduction band is equal to the whole concentration in the valence band. And we defined while discussing intrinsic semiconductor, this equal to a intrinsic carrier concentration number, Ni. So we can write simply N times P is equal to Ni square. That is true. But how about in terms of extrinsic semiconductor? So let me take this. Extrinsic semiconductor, you can have two types. One, P-type semiconductor, or else you have N-type semiconductor. So in this case, how about this equation where we know we have N and P, and of course both are not equal. And even in N-type semiconductor, we have N and P, which both are not equal. And we know in this case N is far less than P, in this case where N is far greater than P. Now how do we show that N times P is still valid as Ni square? Now if you remember, we did a derivation to find the electron concentration in conduction band. While we did the derivation, we never assumed if the semiconductor was intrinsic or extrinsic or anything, right? So we got an expression which said N is equal to Nc times e power minus of Ec minus Ef over Kt, and the whole concentration in valence band was given by Nv times e power minus of Ef minus Ev over Kt. So which means while deriving these two expressions, we never even mentioned was it for intrinsic or extrinsic, which means it was valid for anything. But the only small assumption that we did was we did Boltzmann approximation, which means if we have the energy band diagram like this, where this is Ec and this is Ev, we said the Fermi energy level should be somewhere in between. Let me pick a different color. Somewhere in between these two limits, where the distance between these two, Ec and this level, is at least greater than 3 kT. And even this distance is at least greater than 3 kT, or equal to, in a limiting case. So which means the Fermi energy level should be falling in this range. That was the only assumption that we did while finding the expression for N and P. So now let me take these expressions and find out what is the product of N and P. So N times P is actually given by, let me multiply these two expressions. We have Nc times Nv times e power minus of Ec minus Ef plus Ef minus Ev over Kt. And surprisingly, the Fermi energy level, which is actually different for intrinsic and extrinsic, even it is different for P-type to N-type, which basically gets cancelled here. Which means the product doesn't depend on the type of semiconductor you're looking at, because the Fermi energy level is gone. So if we can represent this, Nc times Nv times e power minus of Ec minus Ev is actually the energy band gap, Eg. So we can show it here. This Ec minus Ef is actually the forbidden energy gap. So Eg over Kt. And of course, we did this derivation while finding the intrinsic carrier concentration, which means this equation still remains the same. And this equation in intrinsic semiconductor is actually equal to Ni square. So in extrinsic semiconductor, it should be exactly same. So this Ni square, this expression that N times P is Ni square, is still valid. And this is called mass action law.